today we're talking about, So today we're talking about two very important quantum protocols, and these are superdense coding and quantum teleportation. These are protocols which are enabled by shared entanglement between the two parties which are trying to communicate. So last week we talked about the maximally entangled states. And these, we saw that they display perfect correlations when measured in complementary bases. So we talked about the computational basis, so the 0 and the 1. Well, we also call it a Z basis, as well as the X basis, which is the plus and the minus state. So last time we were discussing mainly the phi plus state over here, so the 0, 0 plus 1, 1. But in fact, for dimension 2, that is a 2-qubit system, there are 4 maximally entangled states. So these are the 0, 0 plus 1, 1, the 0, 0 minus 1, 1, the 0, 1 plus 1, 0, and the 0, 1 minus 1, 0. So because we are in dimension 4, therefore we need 4 states to span the Hilbert space. So you can check for yourself that these are all orthogonal, and you can also very easily check that we can apply local single qubit unitaries to convert between them. In fact, I think we'll do some of these on the board. So the phi plus is just the phi plus, and if you apply the Z operator to the phi plus, you end up with the phi minus. If you apply the X operator to the phi plus, you end up with the psi plus. And if you apply the X and the Z, you end up with the psi minus. So we'll do some of these on the board now. Okay, pen's hiding there. So the 4 states that we wanted were, okay, so I think I'll omit the one of the square root 2 for clarity. So we have 0, 0 plus the 1, 1. We have 0, 0 minus 1, 1. We have the 0, 1, 0, 1 plus 1, 0, and then we have the 0, 1 minus 1, 0. So to go between these two, we want the Z operator, which is which is a 0, so this is an operator, so it deserves a hat, minus the 1, 1, tensor the identity. So this tensor identity just means that I'm doing something to my first qubit and leaving the second qubit alone. So if we apply this thing to the first qubit, we have 0, 0. We have 0, 0, minus 1, 1, acting on 0. Sorry, I'm just writing this out slightly more carefully. Oops, this should be qubit 2, 0, 1, 0, 2. So the subscript there just means that you have qubit 1 and qubit 2, and I'm also omitting the identity. It just means that it passes straight through the second one. So these all act on qubit 1. Okay, there. So this 0 acts on that one to give you a 0, and then you end up with a tensor on the second one, because so this thing will act on this thing. Oops. Okay, let's do it. Okay, let's write it out. So you have 0, 0 acting on 0, 0, minus 0, 0, minus 0. Wait, sorry, there should be a 1, 1 over there. My bad. Acting on a 1, 1. So you have a 0, 0, acting on a 1, 1, minus 1, 1, acting on a 0, and plus, wait, sorry, there should be a plus. That should be a minus. Is that right? So you have your 0. Wait, what am I doing? Okay. Sorry, start again. So this first term is correct. The second term, you have 0, 0, acting on the 1, 1. And then you have a minus, a 1, 1 bra, acting on the 0, 0, minus the 1, 1, acting on the 1, 1. Okay, so now I'm just going to put in, okay, maybe I'll just leave the subscript as it is. So this will give you a 1. Okay, different color. So this will give you a 1. This will give you a 0. This will give you a 0. And this will give you a 1. So what you end up with is a 0, 0, minus the 1, 1, as we wanted. So when you act the Z state on the 0, 0 plus 1, 1, you end up with a 0, 0, minus 1, 1. So I hope that's clear if I'm just, or it becomes clear if you stare at it for a bit longer. There is a slightly more elegant way of doing it, or you can do it in matrix notation, which I'll repeat just to hammer it in. So remember that we can also write. So remember that we write alpha 0 plus beta 1 in vector form as alpha beta. So if I have this thing plus 1, 1, now I can write this in vector form like that. So you have a half, you have a 1, 0, 0, 1. So remember, like when we take a tensor product, these columns correspond to the components 0, 0, 0, 1, 1, 0, and 1, 1. So now when we have a Z operator, just given by this thing, so tensored with the identity, which is just ones on the diagonals. So this is equal to, so you're literally writing down matrix blocks. So you have a 1, 1, 0, 0. That corresponds to this 1 multiplying by everything over here. And then you just have zeros, you have zeros, and then you have minus 1, minus 1. Okay? So this thing acting upon 1, that should be obvious. That this becomes, let's normalize, a 1, 0, 0, minus 1 with a factor of square root 2. So that's that exercise. Now let's have a look at the X operator. So X operator is given by ones on the diagonal. So now when we multiply it by the identity, this is 0. So this would give you, so the identity, okay, let's just write it out so that you see it on the board. The identity. So you have a block of 0 there, and you have this identity on this block. So the 1, 1, 0, 0. You have this block, which is 1, 1, 0, 0. And then this block is just 0. So now if I act upon state, this, when you do the matrix multiplication, okay, let's just do that properly. So you have 0, 0, 0, 0, 0. So the first term is 0, 0, 0, 0, 1. So the second element is 1. So the third element, you have 1. So the fourth element will just be 0. Okay, I'm going to put in the normalization factors. So this thing is equal to the 0, 1 plus 1, 0. So now we have converted from the 0, 0 plus 1, 1 to this thing. So I won't do the other one, because if I now apply the Z gate, that'll just put a phase in the middle here. So it should be noted that this X is a single qubit element. So it doesn't matter whether Alice applies this to the qubit or Bob applies to the qubit. Because if you look at it, if one X gate is applied, it just means that you're flipping either the first 0 or the first 1 or the second 0 and the second 1. So if you flip either of these, you end up with this state. Okay. So that's that. Stop presenting. Let's go back to the slides. Okay. Okay. So those are the operations. You either have a Z, an X, or an X and a Z. So now the protocol for teleportation, not teleportation, for superdense coding, as we were discussing before, is that Alice wants to send a single quantum state to Bob, i.e. 1 qubit, but she's able to send 2 classical bits after Bob receives her qubit. So the protocol is as follows. So given that Alice and Bob share a quantum state phi plus, so the 0, 0 plus 1, 1, Alice wants to apply one of the 4 unitary operations, so the identity, the X, the Z, or the XZ to one of her to her share of the maximally entangled state. So now she transmits her qubit to Bob using a noiseless channel. So we're assuming everything's noiseless here. So upon receiving Alice's qubit, Bob now is in possession of one of these 4 states. So since they are orthogonal, Bob can project them onto the Bell basis again. So we've talked about measuring things in the plus basis or the computational basis, so the X or the Z, but this is also equally allowed. So he's quantum mechanically allowed to project the state onto one of these 4 bases, and since these are orthogonal, the outcomes are deterministic. So Bob will get a click in either the plus or the phi plus, the phi minus, or the psi plus or the psi minus, and depending on the outcome, that will simply correspond to Alice's message. So for example, Alice and Bob can agree on the fact that if they have a plus, they will call that a 0, 0. If they have the phi minus, they'll call it a 0, 1. And a psi plus, they'll call it a 1, 0, and a psi minus a 1, 1. So the classical bit contains 2 bits, but Alice, in this case, has sent over a single quantum bit. So I hope that sounds weird to you, because this is strictly prohibited classically. Okay, so now, how does Bob actually perform this Bell state measurements? So I think everyone's just happy with the fact that I can measure in this computational basis. But how do I measure in this basis? Okay, well, so I think you are happy with the concept of the unitary operation. So what I'm trying to say is, wait, let me go back to the screen over here. Stop presenting the window. Okay, so I think everybody's happy with the fact that I can, so I have a quantum state. Okay, let's go back to the black. So I have a quantum state. I can project. Okay, why is my pen so slow? I can project this onto the 0 or 1 basis. In fact, I can project it onto the 0 and 1 basis of many qubits, as many as I like. So these just, and I think now people are also happy with the fact that I can apply unitaries to states. So if I have quantum states, psi dash, that's equal to a unitary acting on psi. And I can definitely also measure psi dash in the computational basis, right? So I can do something to the quantum state first, and then I can measure in the computational basis. So if you're happy with that, then I can show you that there is an operation which will allow me to go from, let's go back to this window. Which will allow me to go from the computational basis to the 0-1 basis to the Bell basis. And this is the unitary that we need. So you can check for yourself that you're happy that this is a unitary. So you just have to check that U and U dagger multiplied by U gives you the identity. So what this is actually just a beam splitter operation on the first qubit, tensored by an identity on the second qubit. So this is a 4x4. So the first part of this is a 4x4. And then this is concatenated with this thing over here. So it's 2 1s on the first 2 components and 2 1s on the off diagonals. This is what we call a CNOT gate. So this is a controlled NOT gate. So you can satisfy yourself that this is also unitary, that's allowed. When you multiply those 2 things together, you end up with the U decoder. And oops, if you act the decoder upon one of the 4 Bell states, it will convert the Bell state, so the phi plus and minus and the psi plus and minus, into a 0, 0, 0, 1, 1, 0, or 1, 1. So upon receiving the state, Bob can simply apply this unitary onto the state, and then obtain the measurement outcome corresponding to the classical bits that Alice has sent him. Okay, so that's the super dense coding protocol. Are we happy? Are there any questions? Okay, so if there are questions, feel free to email me. And now I want to move on to talk about quantum state teleportation. So I think this has attracted a lot of interest even outside the physics community just because of the name teleportation. I often get asked in a pub, so can you teleport me into a gold vault or teleport gold out of the vault? So the answer to the first question, which I often give, is that yes, I can probably teleport you into a gold vault, except I will have to kill you first. And we will actually see what that means physically. We'll see what that means mathematically. So let's start by stating what quantum teleportation is not. So firstly, it is not science fiction, and it has been demonstrated in the lab again and again, everywhere in the world. And it cannot dematerialize an object in one location and make it appear at another. So what we're teleporting is not mass, but the state. So the information on the state, if you like. And once again, it cannot transmit information, classical or quantum, faster than the speed of light. And we will see at which step in the protocol exactly that prohibits the superluminal communication. So this is the task. So here we want to assign Alice the task of sending Bob a qubit that is prepared in an arbitrary superposition of alpha 0 plus beta 1. So we want to actually put some strain on the task, which will make it seem like initially that is impossible. So here, we want to require that Alice does not know the coefficient alpha and beta, so she doesn't actually know what the quantum state is. Now, we've seen before that, that it's actually impossible to clone an arbitrary quantum state. So we allow Alice to send precisely 2 classical bits to Bob, so 00, 01, 1011. We've seen this before, as in the dense coding. However, we are not going to allow further quantum communication between Alice and Bob. So Alice is actually not allowed to send the state directly to Bob. So given these constraints, it might seem to you that it is actually impossible to complete this task. But now we will proceed to show that it is possible, because Alice and Bob pre-share a maximally entangled state. So if you think about what this means slightly more carefully, right? We are saying that Alice is allowed precisely 1 copy of the quantum state, alpha 0 plus beta 1, but she doesn't know what it is, so she's not allowed to measure it. And even, okay, so if she is only allowed 1 copy, it means that she will, no matter what measurement that she chooses to do, she will obtain 1 outcome. So she cannot figure out what alpha and beta are. And even if she does know the quantum state, alpha, beta plus, so what alpha and beta are, these can be arbitrary complex numbers. So in principle, if she knows what it is, she can send a really long classical string to Bob telling him exactly what these coefficients are. But unfortunately, she's only allowed to send 2 classical bits. Right, okay, and the no further quantum communication is allowed between Alice and Bob. Is stating that she's not allowed to send this state to Bob. That could be a constraint stemming from the fact that the channel between her and Bob could be very noisy or very lossy. So if your quantum state is very precious, then you don't want to potentially lose it in the middle. But what they can do is to pre-establish a maximally entangled state and then accomplish this task. And now we will proceed with the protocol. So the initial state is psi, the one that we want to teleport, tensored with a maximally entangled state that's pre-shared between Alice and Bob. So the subscripts there, A1, means that Alice is in possession of the state. And here, A2 means there's a second qubit that's in possession of Alice. And then the third qubit is in possession of Bob. So this one is, remember, is shared between Alice and Bob. So the total state can be written like this. So you have alpha 0 plus beta 1 belonging to Alice, tensored with 0, 0, 1, 1 belonging to A2 and Bob. So we can expand this out. And the end product is given by equation 5 there. So you have alpha 0 tensored 0, 0, giving you this first component. And you have alpha 0 tensored with 1, 1, giving you the second component over there. You have the alpha 0 you have the beta 1. Wait, sorry. So alpha 0 with 0, 0, giving you this component. Alpha 0 with the 1, 1 gives you this component. The beta 1 with the 0, 0 gives you this component. And the beta 1 with the 1, 1 gives you this component over here. So I'll give you a few seconds to stare at that equation. So this is just writing out different components. Okay, so now remember, Alice is in possession of the first 2 qubits. And now she will project her bait qubits onto the Bell basis. So don't think about how this is implemented physically, just sort of accept for now that she's allowed to do this because it's allowed quantum mechanically. So the blue just highlights which qubits Alice has. So now we want to use the following identity. So because, so for example, let's look at the 0, 0 state. We can write it as a 0, 0, or we can switch bases and write it as a superposition of the phi plus and the phi minus state. So let's do 2 of these to convince you, or just to make sure that you're happy with it. So we have so we have phi plus is equal to 1/2 0, 0 plus 1, 1, and the phi minus equal to 1/2 0, 0.
The screen isn't up on the Google.
Sorry.
It's okay.
Okay, this is good to know. Oops, okay, there we go. Okay, so I'm just writing out the phi plus is equal to the 0, 0 plus 1, 1, and the phi minus is equal to the 0, 0 minus the 1, 1. So once again, yeah, for this entire course, we're just playing with zeros and ones. And so, of course, when I add these two together, so I have phi plus phi minus will give you a 0, 0 plus 1, 1 plus a 0, 0 minus a 1, 1. So now there are normalization factors. There are normalization factors in front of these things. So now if I put the correct factor in front of it, that would just give you a 0, 0. Okay, so this is just a trick. Right, window, I want to bring up this thing. Okay, so now the presentation should be back. So we are applying these tricks, and we want to say that we substitute this particular state, or this expression for the 0, 0. We are substituting this expression for the 0, 1. We are substituting this expression for the 1, 1, and this one for the 1, 0. Okay. So now when we do that, you can see that the initial state, so remember this expression over here with some of these things highlighted in blue. So remember that nothing has been done to it at this point. So this is just the initial tensor state between the state that Alice wants to teleport, so the alpha 0 plus beta 1, and the maximally entangled state that's shared between her and Bob. But now that we've rewritten it in this form, we can see that there is a psi plus here that's in front of the alpha 0 plus beta 1. there's a tensor product in the middle here, which I've omitted for clarity, and there's a phi minus in front of the alpha 0 minus beta 1. There is a psi plus in front of the alpha 1 plus beta 0, and there's a psi minus in front of the alpha 1 minus beta 0. And now let's write this as an even more compact way. So you have a phi plus tensored with psi, the original state that Alice wants to teleport. And now, just take note that there is now a beta subscript in front of psi. So this is saying that Bob is in possession of this state, right? So this is saying that if Alice is in possession of a phi plus, then Bob has the state that Alice wants to give to him. But it's not just this component. We have all four possibilities. So you have a psi minus and a z operator applied to the original state. And if Alice is in possession of psi plus, you have an x operator applied to the original state, and so on and so forth. So if Alice has a psi minus, then there is the z and the x applied to the state, the original state, right? So remember, once again, nothing has happened at this point. I'm just writing out the original state that Alice wants to teleport with the state that they share, the maximally entangled state that they share. So this is just mathematical trick to write the state in a different form. So now magic happens. So the first two the first two qubits Alice will now project onto the Bell bases that we just seen. So here, Alice puts together the state that she wants to teleport with half of a Bell state. She performs her measurement. And now, remember, when she performs the measurement onto the Bell bases, she will get one of these four answers, each with equal probability. So she will either obtain a phi plus, a phi minus, a psi plus, or a psi minus. So now she transmits 2 bits of classical information to Bob, which indicates which of the 4 measurement outcome has occurred. So these are, so remember from before, the teleportation protocol, the 0, would correspond to the identity. The 0, would correspond, say, the Z. The 1, would correspond to the X. And the 1, would correspond to the Z and the X. So if you look at this state here, so Alice has measured her first 2 qubits, right? And it will collapse it to one of these 4 states. And since the state has this structure, as soon as she's got a measurement outcome, so for example, she got an outcome to say that, oh, she got a phi minus, she immediately knows that the state that Bob has is a Z applied to the original state that she wants to teleport. So this is this state over here. And so on and so forth. If she got a phi plus, then she knows that Bob has the state, the original state. If she got a psi plus, then Bob's state has the X applied to it. And if she got a psi minus, then Bob's state has the Z and the X applied to it. So, and now she will transfer this information to Bob. And Bob, upon receiving the classical information from Alice, he will apply one of these 4 operations. And now Bob is in possession of the original state that Alice wants to send him in the first place. If you think about it, number 2, so the step number 2 there is precisely the step that prevents Bob, that prevents the faster than light communication. So remember, the collapse of the wave function is instantaneous. However, if Bob is not in possession of the knowledge, so, what occurred to Alice, so the identity, the X, the Z, or the XZ, then effectively what Bob has is a combination of all of those applied to the state. And that state is what we call a maximally mixed state. And that particular thing has no information whatsoever. So if we were to do the maths properly, you will see that if we were to mix these 4 states together, then the final state is independent of the coefficients alpha and beta. Whereas if Bob is given this information, then he can restore alpha and beta perfectly. So that's the end of the quantum state teleportation protocol. Are there any questions? Or was that clear? Or did I lose you at some point?
I mean, I feel like it might just be because I was taking it as the wrong type of teleportation.
Yeah, okay.
I think I have that sci-fi look, sort of, not teleportation, not the more. I feel like the quantum teleportation is a bit different to what I imagine it. So
yeah. So here, okay. So what you're teleporting is not the actual object, but the state of the object that it is in. So, right. Originally, Bob already has a qubit on his side, right? So the protocol doesn't transfer mass, but it transfers information on the mass. Sorry, it transfers information on the state.
Okay, I get it now.
Okay.
That makes more sense.
So what do I mean when I say that, I could probably teleport you into the gold vault, but I have to kill you first? So obviously, the first step, Alice has to project on this projector state onto a pure state, right? So this is effectively making a measurement. So, and she's then sending classical information on the other side. So, the not so good analogy is that I have to kill you first, and then I'm sending classical information onto the other side, and then the other side will reconstruct you from whatever information I'm giving them. So yeah, you probably do not want to be teleported. So yeah, so that's the protocol. It is real because it has been demonstrated again and again. And because there is this classical step in the middle where Alice has to send state to Bob, and obviously this bit cannot occur faster than the speed of light, therefore the protocol cannot be completed faster than the speed of light. So yeah, so it might be slightly anticlimactic if you're thinking about science fiction, but that's what we can do in the lab. So, okay, we are pretty on time. So I've actually completed the formal material that I've written. So for next week, so Monday is supposedly a public holiday. So Thursday, this time next week, I think I will talk about some of the hacking or some of the ways people have been trying to hack QKD systems and why QKD systems or quantum key distribution systems, why they are not perfect yet. And I'll probably talk about the broader field of quantum technologies and the major fields, and I'll probably do some more math on the board. And I'm actually open to topics that you're interested in. If you want to send me suggestions, or are there any particular questions about quantum technologies that you want to ask? So you may send me emails. Okay. So yeah. So any more questions? feel free to drop me an email. If not, I'll see you next week on Thursday, I guess.
Thank you for it.
Cheers.